In a certain game, players 1 through 5 take turns rolling a standard 6-sided die, beginning with player 1. If a 6 is rolled, then player wins. If any other number is rolled, the die is given to the player whose number corresponds to the number rolled, even if that is the player whose turn it currently is. What is the probability that player 1 wins? Express your answer as a common fraction. So, how are we going to solve this problem? So we need the probabilities that the player 1 wins. Let's calculate all the possible ways player 1 can win. So first of all, player 1 can throw a 6 right away, and he wins. Well, that's one way. That's the way how he can win in just one throw. So now let's think about how he can win in 2 throws. Well, the first throw has to be 1, so he has a right to throw a second time. And the second throw obviously has to be 6. That's how he can win in 2 throws. Now what about 3 throws? Well, obviously the last throw has to be 6. Then the one before that has to be 1 because he has to get a right to throw. So the last 2 have to be 1 and 6. And what about the one before that, the first throw? Could it be 1? Yeah. Could it be 2? Sure. Could it be 3? Yeah. 4? Yeah. 5? Yeah. 6? No. Because if somebody throws 6, the game is over. Okay? So really, to win in 3 throws, it should be any number except for 6 first, not 6, then 1, and then 6. What about 4 throws? Similar story. The last 2 throws should be 1 and 6. And the 2 before that could be anything but 6, because again, 6 ends the game. So what about 5 throws? Well, same thing. The last 2 are 1, 6, 3 before, not 6, okay? So, and we can continue going this way, you know, if we want to win in 6 throws, 7 throws, 8 throws, and so on. So basically the idea is the last 2 is 1, 6, the previous one's anything but 6, okay? And let's calculate probability of each of those positions. So throw is 6. What's the chance to throw of 6? Well, it's basically throw one side of dice, which has 6 sides, and we're presumably having a fair die, which means that probability of throw 6 is 1/6. So what is probability of throw 1 and then 6? Well, those events, throwing the first time 1, has nothing to do with throwing 6 second time. So those are independent events. So, and for independent events, probability of having joint event, like first 1 and then 6 together, it's a product of probability of throwing 1 and 6. Both of them have probability of 1/6, total 1/36. Now what's the probability of throw not 6, 1, and 6? Again, those actually independent events. Doesn't matter whether I throw it first, when I throw the second time, and doesn't matter whether I throw in the first and second time, when I throw the third time. So it's a probability of not 6 times probability of 1 times probability of 6. Now what's probability of not 6? Well, we can think about different ways. One way to think about it, well, you can throw 6 or not 6, right? So those are mutually exclusive events. A probability of throw 6 or not 6, one of those is actually 1. You're going to throw one of those. Probability of 6 is 1/6, as we calculated. So probability of not 6 have to be 5/6. So together they give us 1. So in this case we get 5/6 times 1/6 times 1/6. Now what about not 6, 1, and 6? Again, it's probability of not 6, then probability of not 6, then probability of 1, and probability of 6. This is what we're going to get. 3 not 6s, then 1 and 6 in a similar way. First, we multiply 5, 6 3 times, because there are 3 not 6s. And then we multiply 1, 6, and 1, 6, because we have 1 and 6. Okay? Now, what we're interested in is the probability of one of those events happening. Okay? It could be 6 or 1, 6, or not 6, 1, 6, or not 6, 1, 6, 1, and 6, and so on. Those are mutually exclusive events, actually. So if you get 6 first, you cannot get either of those here. If you get 1, 6, we cannot get any of the other ones, and so on. So the probability to have one of those is a sum of probabilities of each of those guys. So what we need to do, we need to add those numbers. But now notice, if you look at this second term, third, fourth, fifth, and so on, each of those terms has 1, 6 times 1, 6. If you pull that out, we're going to get this. And this thing is what? The sum of the powers of 5, 6. Okay? We can write it like this. Now, what you have here is a sum of terms of geometric sequence. We should know the formula like this. That actually tells you what you're going to get if you add these terms of geometric sequence. In our case, this x is 5, 6. So when we look at this formula, all we need to worry about is that x is in these ranges, above -1 and less than 1. 5, 6 is in this range, so we're good. We can use this formula. And if you put x over there, and we get 6. Okay? So this guy, 1 over 1 minus 5, 6, is 6. And now we can see that the probability of winning for player 1 is 1/3. All right? Now, we went through a lot of math finding this answer. Now, is there a way to do it easier, okay, and faster? And the answer is yes. But in order to do this, there's one subtle moment, subtle point that needs to be understood. So let's try to do it a different way. So we know how the player 1 can win. He can win by throwing 6 or throwing not 6 and following, multiple paths. So we can use the following formula that deal with conditional probabilities. So probability of win by first is probability of win given that 6 is thrown times probability of throw 6 plus probability of win given that not 6 is thrown, anything else is thrown, times probability of not 6. So let's go through each term and kind of explain what they are and find the values for them. First of all, probability of throwing 6 is 1/6. We just talked about it. Now, probability of not 6, throwing anything else other than 6, is 5/6. We also know that. Now, what is probability of win if I throw 6? So what it is if we run multiple simulations, what we need to do here is we need to just basically separate all the cases when we throw 6 first. And then ask ourselves questions. What fraction of those cases is the win for player 1? Well, actually all of them, right? If he throws 6, it means that he wins. So probability of win given 6 is actually 100%. It is 1. Now, let's talk about this guy. And that's where the sell point sits. So probability of win if we throw not 6. what we need to think here is there any advantage for the first player in this particular case? So let's just run multiple simulations, millions and millions of simulations, and then just look only at the cases when we don't throw 6 on the first throw. So what can we do? Well, we can throw 1, 2, 3, 4, or 5. There's equal probability to throw one of those, right? So there's equal probabilities that the die goes to player 1, or player 2, or player 3, or player 4, or player 5. So if you think about it, you can also look at this as we having a 5-sided die. If we throw a 5-sided die, well, there's equal chance for either of the players pick up a die and throw further. And well, after we threw the 5-sided die, the player who wins the throw gets 6-sided die, and we just continue playing. So if you think about it this way, you find that there's no advantage for the player 1 in this situation, or player 2, or player 3, or player 4, or player 5. All the players are kind of at the same conditions. So, well, if one of them got a win, but they all have the same chance of winning. In this case, probability of the first player to win is going to be 1/5, right? There are 5 of them. Each of them has equal probability to win. So it means that probability of win by the first one, if not 6 is thrown, is 1/5. And now we multiply all these numbers and get 1/3. Now this is a much faster way of doing it, but there is this point to understand that probability of win, given we throw anything but 6, is really the same for all 5 players. If you understand that, this is the way to go.